Um, I know I'm behind with my pacing schedule. I just wanted to spend time going over the second multiple choice test in your packets, non-calculator. So just want to go through these problems. If you're ahead of me, that's great. You can grab a key and just continue working through. And if you're following the pace up here on the board, then you should either get done or get close to finishing packet 6 by Friday. If you're a senior, you can turn in your packet Friday, you can turn it in next Monday or even Tuesday. Seniors grades are due Tuesday, so ideally I like to get all the senior grades in by Tuesday. So let me know if you have any trouble trying to meet that deadline. Okay. All right. Also, you guys just got back your multiple choice test and your FRQ quiz. I attached the keys to them. I really encourage you guys to look through, see what you missed, and try to understand what you missed, so that the hope is that this is kind of like you obviously got a grade for it, but that this is also a good way to try to figure out what you need to work on or where your potential gaps are, and make those corrections in time for Monday's AP exam. I'll be doing health sessions tomorrow morning, 7:30 and 7:30 Thursday and Friday. So if you have any questions about the packets or your test or your quiz, come by. I can figure those things out for you or go over them. Okay, so this is page 19, the derivative of sine cubed of x squared. We gotta be careful here. Anytime you have a trig function where there's the exponent kind of written in that shorthand form, it's always a good idea to go through a set of brackets. Okay, so get that sign to be rewritten with a set of brackets. So this is, I'm going to say y is equal to bracket sine of x squared cubed. So these mean the same thing, but this is a lot more helpful visually in terms of recognizing, oh, there's some nested chain rule here. I got to deal with the bracket cube. I got to deal with the sine. I got to deal with the x squared. So we're kind of working our way from outside in. So chain rule. So we're taking turns with each derivative here. Outside derivative, bracket cubed. We go through power rule. Keep the inside unchanged. Then multiply by the inside derivative. Sine of u becomes cosine of u times u prime. Okay, answer choice E. Limit as x approaches infinity of x cubed over e to the 3x. There's two ways that you can do this. One way is you can, if you plug in infinity, you'll get infinity over infinity. You can do L'Hopital's rule. That's one option. L'Hopital's rule, most of the time we use it for 0 over 0, but if you get infinity over infinity, that also gives you the ability to do L'Hopital's rule. Another option that we have is using comparative growth rates. So comparative growth rates is where if your numerator and denominator are under different families of functions, different families of functions grow at predictable rates. So LRPE, logs grows the slowest, followed by radicals, followed by polynomials, followed by exponentials. So if I have one over the other, it's either going to be 0 or it's going to be infinity. If the larger growing function is on top, then the fraction is getting larger towards infinity. But if the larger growing function is below, then that fraction is getting smaller towards 0. So in this case, if I do converted growth rates, e to the 3x, that's an exponential. Exponential is growing at a faster rate than a polynomial. So as we approach infinity, this is going to grow much faster than x cubed, and so this is going to approach 0. So that's the faster way of doing it using comparative growth rates, if you can see it. You can also do L'Hopital's rule, where if you plug infinity here, you'll get infinity over infinity, which allows you to do L'Hopital's rule. So x cubed becomes 3x squared. E to the 3x becomes 3e to the 3x. Again, infinity. In for the x's, you'll get infinity over infinity. You keep going, you get 6x over 9e to the 3x. Again, infinity over infinity. Finally, you get 6 is equal to 6 over 27e to the 3x. And now it's going to be obvious that if you put infinity in, this is going towards infinity. This is staying at 6. This is eventually heading towards 0. Number 8, use substitution. So they're indicating what our u value is going to be. Let's pull that 5 outside a set of brackets. Now, notice that they're not solving the problem here. So what that means is when everything is converted to be in terms of u, we got to watch out for the bounds as well. The bounds are also converted to be in terms of u. So right now, everything's in terms of x. Our answer choice, everything in terms of u. So, okay. If you're just coming in, we're on page 19 in packet 6. So it's nice that they're telling us our u value is sine of 2x, but we should be able to know what the u value is going to be after we rewrite it. Right? So I want to make sure that we understand, it's nice that they're telling this to us, but they could also expect us to find it on their own. Right? So the way you can find it on your own, you would, I know you see a set of parentheses around 2x, but the messier your function, the larger your u value is going to have to be. So this is a really large function here. We expect our u value to be a little bit larger. And so if we get that bracket to show up, it's a little bit more clear that this is a better fit for our potential u value. Oh, sorry. Too many twos here. I replace my underlined bracket with terms of u, so u to the fifth. I still haven't resolved the cosine 2x, but we should be able to get the to pair up nicely when we replace our dx in terms of du. Cancel, cancel. There's a 2 left over, but notice the 2's in the denominator. We can push it out as a 1/2. So integral. Oh, sorry. Notice our answer choices are in terms of u, so we're not going to actually do power rule. We're going to leave it alone. But the only thing that is left to adjust is our bounds. Our bounds are in terms of x. We're going to push those bounds through our conversion rate. So let's work on those bounds there. So initially, we started off with lower bound x equals pi over 6. And if we push it through u equals sine of 2x, again, this is non-calculator, so we got to rely on our unit circle knowledge here. So we get sine of 2 pi over 6, which is the same thing as sine of pi over 3. And we know sine of pi over 3, root 3 over 2. That's our new lower bound in terms of u. And then our old upper bound was x equals pi over 2. We push it through our conversion. And the 2 cancel out. We get sine of pi. Sine of pi is going to be 0. So we're going to go from root 3 over 2 to 0. I know it seems strange having the lower bound being the larger value than the upper bound, but if something starts as a lower bound, it doesn't matter what changes or whether it gets larger than the upper bound later, it'll stay as lower bound. Whatever starts at the upper bound will end as the upper bound. Okay, page 20. Number 9, the function f has a derivative given by f prime. What values of x does f have a relative maximum? So relative max we can find by looking at our slope sine line. The nice thing is they're already giving us our f prime, so we don't have to find a derivative. We can just set our f prime equal to 0. Everything's already in factor form, so we can just solve for x, and all of our critical points are here in front of us. So choose values in each subinterval. Here I'll start off to the left of -1. So I'll start off choosing -2. Then I'll choose -1/2. Then I'll choose 1, and then I'll choose 4. They all get inserted into my derivative. It's already in factor form, so that's nice. I can just collect my signs and see whether I'm going to get positive or negative. So -2, and for x, negative. The x minus 3 squared is always positive, so I can ignore that. That's always going to be positive. I can just go check the first and third one. So negative times negative is positive. -1/2 is for x, so I get a negative times positive, which is negative. Plug 1 in, positive times positive. Plug 4 in, positive times positive, positive. So I see a relative max here, I see a relative min here, and I don't see anything here. So relative max is only going to be at -1 because the arrows are kind of showing us how our graph is rising and falling. Let f be the function defined above for what value of b is f continuous. So if I just see the word continuous, then I'm thinking about continuity conditions. I'm going to just step through continuity conditions. So the conditions are, does the limit exist? Does the point exist? Does the limit exist? And then finally, the third condition, does the limit live where the point lives? So we know the point in question is at 2. So let's find f of 2 first. F of 2 is just b. That's just the unknown y value for now, which we're eventually going to have to solve. Second condition, does the limit exist? Notice that x equals 2 is just a point. If you see x doesn't equal to 2, another way of saying that is everywhere except 2. So if you see this, this means everywhere except 2. So that means this is the graph to the left of 2. This is the graph to the right of 2. So if we want to find the limit is just for the graph. We don't do a limit on the point. We just want to do a limit on the graph. So we'll do the limit as x approaches 2. You can do factored form. You can do L'Hopital's rule. If I plug 2 in, I'll get 0 over 0. So if you want to do L'Hopital's rule, you can. So I get 2x minus 7, and denominator was bx minus 2b, right? And if you want to distribute that through so that you have an easier time finding the derivative, bx becomes b, and the 2b goes to 0, right? 2 and b are both constants, so they'll both drop to 0. So the only thing left is b. So reevaluate your limit. I get 4 minus 7, which is -3 over b. So then the third condition is, in order for my function to be continuous, my third condition is these have to agree. So my b has to equal to -3 over b. So I just have to set these equal to each other and basically solve for b. Right? So I can cross multiply. B squared equals -3. And we can't take the square root. If we take the square root and solve for b, we're going to get imaginary number. And in this course, imaginary is considered as undefined. So we're only dealing with a real number system. So in this case, we can't find a value of b that's going to fulfill the condition where a number is equal to a -3 over that number. Between 0 and 6, the graph of f prime is shown. What is the maximum value of the f on the interval? So we have a closed interval. We're asking for absolute max. So this is extreme value theorem here. So that means we got to test endpoints and critical points. If this is the f prime graph, then our endpoints and critical points are going to be the x-intercepts, right? Or sorry, critical points will be the x-intercepts. But we're looking for max value here. So all we need to test are endpoints and relative max. So let me just create a sign line for f prime just so I can figure out what points I really need to be testing. So I'm going to go from 0 to 6. Those are my endpoints. My critical point is at 3 and 5.5. Remember, this is f prime graph, so above means positive slope, below means negative slope. So from between 0 and 3, above the x-axis, so we start off positive slope. From 3 to 5.5, below the x-axis, so negative slope. And then from 5.5 to 6, positive slope. Even though there are critical points at both 3 and 5.5, 5.5 we can ignore because we're only looking for maximum. So there's no chance that a minimum can end up being the maximum value. I mean, it's not wrong if you tested it. It's just an additional step you have to take. So we'll test 0, 3, and 6. And because we're given the derivative and we're given an anchor point, each of these we're going to rely on final equals initial plus displacement to get each of those values. Well, we don't need to test f of 0 because they already tell that to us. So that one we can just set aside. We know that one is taken care of. But if I want to find f of 3, I'm going to rely on my initial point plus displacement. So I know that f of b is equal to f of a plus the integral from a to b of f prime. So in order to get to this piece here, we don't have a calculator. We have to rely on geometric shapes here, area of geometric shapes. So we got a triangle here, 1/2 base times height, 1/2 3 times 2, 1/2 6 is 3. This one here, 1 to 2.5 and 2. So 1/2 times 2.5 times 2. Notice it's below the x-axis, so it should be negative here. So I'm going to get negative 2.5. And then here, 1/2 base times height, 1/2, 1/2 times 2. That's just going to be 1/2. So let's find f of 3. So f of 3 is equal to f of 0, which we know to be 1, plus bridging the gap from 0 to 3 under f prime. So f of 0 is 1. From 0 to 3 is 3. So 1 plus 3 is 4. So that's a candidate. The next one is f of 6. So f of 6, we can say f of 0 plus however much gap we have between 0 and 6. Again, 1 plus, and then from 0 to 6, we have 3 minus 2.5, which is negative 0.5, plus 0.5 is going to give us 0. So we have 1 versus 4. Our absolute max value is 4 if we're comparing our candidates here. Okay, number 12. we have the function y equals 9 to the x with 4 subintervals of equal length. What is the value of the right Riemann sum? So we have to build our interval here on our own. The way we find our interval, our width formula is b minus a over n. This will allow us to split our interval into equal segments. So our width, our a and b values are 0 and 2, and then we want 4 subintervals, so our n value is 4. So 2 minus 0 over 4 is equal to 1/2. So we want our interval to be by 1/2. So here's my graph. 9 to the x is an exponential function, so it looks something like this. So we're going to keep incrementing by 1/2. So 0 to 1/2 to 1 to 3/2 to 2. We want to do right Riemann sum. So we're going to attach the upper right corner of each subinterval to the curve and let them guide the height of each subinterval. So now we just do width times height. So our width is 1/2 for my first rectangle. My height for my first rectangle will be plugging in 1/2 into the function, so it's 9 to the 1/2, which is 3, but I can reduce that a little bit later. Second rectangle has a width of 1/2 as well. Height is whatever this y value is. So if I plug 1 into x to get the y value, 9 to the first power is just 9. Next, width still 1/2, my height. Plug 3/2 into the function, 9 to the 3/2. We can figure that out later. And finally, 1/2 is the width, height. Plug 2 into the function. My function is 9 to the x, so it's 9 squared, which is 81. So we have 1/2 times 3, square root of 9 is 3, plus 1/2 times 9, plus 1/2 times. Now, the way you can do this without a calculator, raising that 9 to the third power is really messy. But we can do this first. We can do the square root first, right? And we know the square root of 9 is 3, and so therefore 3 cubed is 27. So it's a lot easier to do it that way. Shrink the number first before raising it to that exponent 3, and then plus 1/2 times 81. So we can add all this together. We can also do this. You can factor out the 1/2 and then just add up these numbers. It makes it a little bit easier. So if I factor the 1/2 out, I just get 3 plus 9 plus 27 plus 81. So if I combine easier numbers here, 9 plus 81 is 90. 3 plus 27 is 30. So I get 120 over 2, which is 60. Make sure that we don't take shortcuts that we're not allowed to. We can't just say, oh, x becomes 1, 2x squared becomes 2x, and I'll just make it 1 over 2x. We got to go through a full quotient rule here, right? Right. So see that there's something here to distract students to see if they will fall for the incorrect method. So we don't want to think this way. Okay, we got to go through our full quotient rule here. Don't try to cancel anything out. You got to spend the time to expand, FOIL all this out, combine like terms. So you're largely not going to touch this. You're just working on trying to clean up this numerator here. Okay, 14. Velocity of a particle moving along the x-axis is given by v of t. If the particle is at x equals 4, what's the position when t equals pi over 2? So we like to go through anytime particle motion here, you're given velocity, you're given a anchor point. We're going to go through that final equals initial plus displacement. I want to find the position of the particle when t equals pi over 2. So I'm looking for x of pi over 2. I know what x of 0 is because we know the particle is at 4. So we can replace that later. I'm going to write it as x of 0 first. And we got to bridge the gap from 0 to pi over 2 of v of t dt. And normally we plug in the calculator, but this is non-calculator, so we're expected to work this out by hand here. We got to go through use substitution, take the antiderivative, bring our t back, plug in our upper and lower bound, use our unit circle knowledge, get it down to a number, add that to 4, and see what that location is. So we got to do all this by hand here. Use substitution. Sorry, 2 dt equals du. Pull the 1/2 out. Sine becomes negative cosine, so negative 1/2 cosine of u. Bring back your u value, which is 2t. And then you got to plug in your upper and lower bound. So I get -1/2 cosine of pi plus 1/2 cosine of 0. Cosine of pi is -1. Cosine of 0 is also 1. So I get 1/2 plus 1/2, which is 1. So all this work here gets us to 1. We know x of 0 is 4. So we'll put it all together. X of pi over 2 would be 4 plus 1, which is 5. Okay, page 22. The function y equals g of x is the differentiable and increasing. On what interval is the function g of x cubed minus 6x squared increasing? So anytime we're talking about increasing or change, rate of change, we have to involve the derivative. So we know we got to involve the derivative. So let's find the derivative. Now, what's strange about this is that this is a function that is stuck inside a function notation. So it's basically g of u. So to find the derivative, we'll do chain rule because we know that g of u's derivative is g of u times u prime. So a little bit of chain rule here. So outside's derivative, g becomes g prime. We keep inside intact. And then multiply by the outside's derivative. Sorry, inside's derivative, x cubed minus 12x. Now they're telling us that g is always increasing. So we know that this g prime will always be positive. So basically, don't have to worry about it. But to find, we want to create a slope sign line so we can actually gather information. So it's going to all come from here. This we can actually work with and actually set equal to 0 and solve. So I'm going to get it into factored form, but I can't do anything with this. This whole g prime is just, but we know that g is increasing, so therefore g prime is always positive. Don't have to worry about it. Just have to figure out these critical points from here. So I can factor out an x squared. I'm left with x minus 12. So my critical points, x, factor out an x, and I get x squared minus 12. Is that right? My bad. I didn't finish taking the derivative here. So x cubed becomes 3x squared. Let me try again. Okay, so outside's derivative, g becomes g prime. We keep the inside intact, and then we take the derivative of the inside. X cubed becomes 3x squared. 6x squared becomes 12x. We can factor a 3x out. I'm left with x minus 4. So I can set 3x equal to 0. I can set x minus 4 equal to 0. And I get x equals 0 and 4. So I'm going to place them onto my slope sign line. And I'm going to test my interval here. -1 to the left of 0, 1 between 0 and 4, and I'll choose 5 to the right of 4. Again, no need to plug into here. We know this is always positive because our function is increasing. So this is always positive. Plug -1 in for x, so negative times negative is positive. Increasing. Plug 1 in, positive times negative is negative. Decreasing. Plug 5 in, positive times positive is positive, increasing. So increasing would be in this interval here from -infinity to 0, and then from 4 to infinity. Answer choice A. I want to make sure to go over 17, so if you can flip over to 17 here. We have a function ae to the negative ax. Treat a like we would if it was like a 2 or 3. So imagine if this was like y equals 2e to the negative 2x, right? It's a lot easier to think of it in terms of this. And this you would just make it e to the u times u prime. You'll bring down the -2. So same thing here. You just treat a like you would if it was a 2 or 3. So y is equal to ae the negative ax. So my derivative, we know the 2 would stay. So same thing, we'll make the a stay. Normally you would say e to the u times u prime. So e to the -2x times -2. Same thing here. E to the negative ax times -a. Merge the a's together. Okay, so I'm not quite moving at the pace of this pacing schedule is more for seniors to be able to finish the packet by Friday. I know that juniors have a bit more time, so but I just want to kind of make sure to go over multiple choice problems from previous AP exams. Just kind of spend time with them. So hopefully you guys can still make progress. Tomorrow I'll continue picking out problems. But you guys can come get your phones and you can return your keys as well.
Oh, right. Absent today.
Okay, sorry.
No, no.
Okay.